we're still on, and we still will be for today, how to do partial derivatives. I think last time, if my memory serves me right, we looked at second and third partial derivatives, and we had the funny notation. So I'll just remind you how that goes. If I had a function f, I won't even tell you what it is, and I said, calculate that, that would be a third partial derivative, wouldn't it? And wouldn't you do with respect to x first, with respect to y second, and with respect to y third, right? It would be written down using that notation in that order. And we mentioned there's a really cool guy called Clairaut who proved why this property is true, but didn't he say that you can do any of these in any order you like, and the answer will end up being the same, with a caveat. The original function that it came from has to be continuous. If that original function has a discontinuity, then at least in some situations, in some values of x, y, right, it will not match. We mentioned that, right?
Yeah, and
it's called Clairaut.
And just for clarification, it's continuous on the range that's you're evaluating at, right?
Yes, it's continuous on the part of the function that you're looking. Because functions might be discontinuous. So you could say continuous on the domain might be a simpler way of saying the same thing. Right. Now, that is totally correct. So I'm going to start by doing Calc 1 and looking at differentiating certain unusual functions, so that when you come to the partial derivative version, you'll be able to do them. So this one is not a difficult one. We all know how to do the derivative of that fella, right? We're talking Calc 1 world, right? So there's no partial derivatives in the world, right? That you know. What's the derivative of the inverse sine function? No, it's not the inverse cosine function.
Isn't it like 1 over the square root of x? I can't remember, it's x squared plus 1 or x squared minus 1?
Keep permutating through, you're close.
1 minus x.
There we go, somebody in the background. Okay, so if you see an inverse sine function and you want to differentiate it, it's 1 over the square root of 1 minus whatever the variable happens to be squared. Now, oops, wrong one. Let's come in there. We all know that one. It's a power rule. But what's the derivative of that one?
Um, 3 to the x natural log of 3.
Nailed it. So there are some, I don't know, I deliberately chose this one and this one because I was looking through some of the homework questions and I know those guys appeared. And so we have to be aware of how to differentiate them. So that's a little, I know, a little side issue covered, right? There are some unusual derivatives that you may have been a bit rusty on, you know, inverse sines of things. So let's put them into an expression. Suppose we had z equals the inverse sine of x squared plus xy cubed. And we would like to know the partial derivative, say, with respect to x. Now, the derivative of an individual sine of something is 1 over the square root of 1 take away something squared. And I'm using this x as a placeholder, so that's why I'm calling it something. So won't this be the placeholder that goes in there? So it will be 1 over the square root of 1 take away this horrible mess squared. But isn't this also a chain rule? And since we're doing a partial derivative with respect to x, don't we have to differentiate this with respect to x then? And with respect to x, you get a 2x, and with respect to x, you get a y cubed. And there's really nothing worth fixing here. Me personally, I don't think there's any advantage in squaring that and sticking it inside the square root. In fact, see if you square that and stick it inside the square root, won't it look even uglier than it does right now? And I don't see any factoring in the top. So pretty much that's the end of style points. In a funny sort of a way, do you know really ugly functions don't have very many style points? And there's very often not a lot you can do to them. They just end up looking ugly and they stay ugly. So imagine that you had, I'll do 3. That guy. And you wanted to find the partial derivative with respect to, say, y. Now that falls under this one here, right? So if you wanted to do, well, where is it? Right. If you wanted to differentiate this guy, then you get the 3 to the x log 3, right? That's what this guy is. But think of that as a placeholder for x. So what you get is 3 to the power of x sine y times the natural log of 3 times the derivative of the power. And with respect to y, this fella becomes x cosine y. Now there is a minor cosmetic fix to style points. And it isn't the rule for style points simplest to ugliest. So I would start with a log 3 because it's a number. I then do an x. I then finish with those two guys here. And that would be considered, you know, a good format for the answer. So we happy with inverse signs, 3 to the x's, in the kind of the partial differentiation world. We good? Let's show you some other bits and pieces. There's lots of There's lots of bits and pieces to partial differentiation. There are a lot more versions of it. Here's a version. That is not a 3-dimensional function. That's actually a 4-dimensional function. X, Y, Z are independent variables, and W is the dependent variable, right? So there's 4 of them. If you try to sketch that, you would have to create a 4th-dimensional graphics card and adapt your brain to see in 4 dimensions. So the short answer is you'll never see what that looks like. But that doesn't mean we can't do its derivatives. So if I asked you for a partial derivative of this guy with respect to z, then from here you would get 2xyz, and from here you get negative x sine z. Do you see that you can extend partial derivatives to as many variables in the universe that you want? At least theoretically, can't you? Suppose I had a function called f, and I wanted this function to have 10 variables in it. You know, you start running shorty letters of the alphabet pretty quickly, because don't a lot of letters get used? E, for instance, gets used as a power. You really shouldn't use A, B, and C's, because don't A, B, and C's typically get used to represent constants? You know, you're going to run shorty variables. So how do they get around it? Well, they do this. I've just given you the equation of the length of an object in 10-dimensional space. Each variable is given a little subscript. So x1 is like x, and x2 would be like your y, and x3 is like your z. Do you see, by using this notation, couldn't I do a 200-dimensional function if I felt like it? I believe in string theory is up to 11 dimensions in some situations. So we've got the math, and we can do the partial derivatives, which if you're doing 11-dimensional functions and they're not space curves, you'll need to be able to do partial derivatives in them. Kind of interesting. Here's a guy. Called the Laplace equation. Named after the same guy who did Laplace transforms. Anybody done differential equations? Differential equations? Nobody?
A little bit.
Right. Did you get to, it's either 1 or 2, I'm not sure where it is. I think it's in 2, but do you do a guy called, I think called Laplace transforms to help you solve them?
No, sir.
Okay. Well, anyway, it's the same guy. So he did a couple of things and they get named after him. Here's this particular one. Imagine a 2-dimensional function for no reason I can think of, but they're always called u. And it has this property, that its second partial derivative with respect to x, add its second partial derivative with respect to y, and you end up with the answer 0. So you can imagine that these two second derivatives are the negatives of each other. Now we know that xy and yx are the same, right? But if you add them together, you always get something, right? It's not like one's a positive and the other's a negative. So, but what this is saying is that this second derivative is the negative of this second derivative. And second derivatives are typically quite different from each other, right? If you write down a normal random function of x and y, and you do its second derivative with respect to x, and then you do its second derivative with respect to y, they'd be quite different, wouldn't they? Okay. So he had discovered that there are a family of functions that this property is true for. And what's cool about them is that they solve what's called the wave equation, which is a classic problem in physics. And what it does is it allows you to model waves. And waves are big things in physics because radio waves and light waves and, who knows, magnetic waves and gravitational waves and lots of things move like waves, don't they? And so if you can have an equation that allows you to model these things, it's a pretty cool thing to have. It's essentially a differential equation. It's saying the second derivative with respect to x plus the second derivative with respect to y should equal 0. And people go hunting for versions of that guy. Let me show you that guy, because there's a question in the homework with that guy in it. So let me see if I can find him. Has anybody heard of the wave equation, just off the top of my head? It's a classic problem in physics. No? Okay. It's a pretty cool problem, which is pretty good for me because normally I don't like things that are practical. There we go. Are you looking at question 15 here? Right. So here we got Laplace equation. Here is a whole load of functions, some of which work, some that don't, and your job is to find out which ones do. Can I just tell you that that one works and move on, because I know it's got a cosine, a hyperbolic cosine and sine, and I know I said I'd avoid it, but this question is so cool, I kept it. So when you do your version of 15, the one that has a hyperbolic sign and cosine in it does work. Okay, there are 5 more guys. Pick one at random. Just tell me one and we'll go through the process and we'll see if it works or not.
Start at the
Actually,
top. Natural log of the quantity square root x squared plus y squared.
okay, so I'm now going to leave that and go in, and this is what you would have to do. If you're doing it properly and you want to actually learn something from it. You're going to differentiate this, right? Twice with respect to x and then twice with respect to y. I'm not going to do that yet. Would you agree the square root is the same thing as a half power? Would you also agree that a half power can be written like this? Remember the rules? That is much easier to differentiate than this is. Would you agree? So that brings me to a rule that I have names for rules, my own rules at least. And this one falls under the category, just because you can doesn't mean you should rule. Could I have left it originally as is and find all its derivatives? And the answer is yes, I can do that. But just because I can do it, does it mean I should? Well, not if there's a better version of it that's got less work. Would you agree? Just because you can do it doesn't always mean you should. And that gets its, the history behind that comes from my mum. I sing in the shower. I am an atrocious singer, so you will never hear me sing, but I do sing in the shower when I was younger. And my mum would bang on the door of the bathroom, and she would tell me, just because I can sing doesn't mean that I should. And so that's where that saying comes from. Do you know there are some people who can sing, and I'm one of them, who really shouldn't? Right? So that's where that comes from. So let's do the math of it. If you differentiate with respect to x, what do you get? Well, you get 1/2, 1 over the guy, times with respect to x, the derivative. But do you see those two guys play well together? And you get that guy, don't you? Right, the 1/2 and the 2 gives me x. Now, to do the second derivative, would you agree that since there's an x on the top and an x on the bottom, I'm going to have to do a quotient rule on that. So it's going to be f dash g, take away f of g dashed, all over g squared. So it's going to be 1, leave this guy alone. Take away, leave this guy alone, and differentiate the bottom with respect to x, and you get 2x. And then the bottom guy squared. And that gets you. Anyway, the bottom line is you end up with that guy. So far, it's all good. So here is this fella. If I wanted to do u, a partial derivative with respect to u twice, I could just go back to the start, couldn't I, and do the same kind of working, but I'm not going to. Is this a symmetric function? And remember the trick, the shortcut with symmetric functions? Can't you predict the other derivatives by just switching the x's and y's around? So won't this become x squared, take away y squared? And won't this become technically y squared plus x squared? Ah, but to heck with it, isn't that just x squared, y squared anyway, squared? Now let's put these together. If you take the first fella, he looks like this. If you add the second fella, he looks like this. They share a common denominator. Oh, you get killed by that. That gets killed by that. Hey, it works. Cool. So this function satisfies the wave equation. So it's called the wave equation anyway. Evidently, it models some kind of very interesting wave. A weird looking wave to me, but I'm not a physicist, so I don't care. Okay, I'm only going to do one more of these guys. So as usual, we'll randomly pick them. So in this case, I would put a check mark on that one, right? Right, so at least that homework question's done for you, because there's a lot of work in these ones. We've got 4 more guys to pick from. Not all of them work, by the way. There are some failures. And maybe I won't pick a failure because you're choosing. Of the 4 that's left, which one do you want me to do next?
e to the negative x cosine y minus e to the negative y cosine x?
No, I'm not doing it. It sounds very cruel. Because that's the hardest one of the set, and I'm lazy.
That's why I picked it.
I don't blame you. I would have chosen it too. I'm going to pick x squared plus y squared. I want you to get practice as well. You know, if I'm being fair, I want to do that. X squared plus y squared, isn't it symmetric?
Yes.
Can you imagine doing a differentiation with respect to x twice? Don't you just get 2? Right, x squared becomes 2x becomes 2. I'm doing it in my head, but you agree? What would the derivative of x squared plus y squared be if you did a double derivative, partial derivative with y's? Well, the first time you'd get 2y, and the second time you'd get 2. So wouldn't that one just become 2 plus 2 and it wouldn't work? What about x squared minus y squared then? Could do that in our head, couldn't we? Would that almost be the same, but wouldn't it be 2 take away 2? That one works, that one doesn't. So what does that tell me? Well, it tells me something quite interesting. It would have been nice if symmetric functions solved Laplace's equation, but can you see that one did and it's symmetric, and this one didn't and it's also symmetric. So that means Laplace equations might be symmetric, they might not. They might kind of look like each other, and then they might not. Which means that you could probably spend your entire life just finding various solutions, because there actually, I believe there's an infinite number of solutions to Laplace's equation, which probably means that there's an infinite number of different waveforms out there. I don't know how much insight that's into the universe, but evidently if you looked hard enough, you could find all sorts of weird wave properties to do with, you know, maybe magnetic waves behave in a really weird way. I do know, come off the top of my head, aren't electrons considered as particles? Aren't electrons also in some situations considered as waves? Which means they behave, according to the math, in 2 totally contradictory ways. That's kind of scarily mind-blowing if you actually delve into it. Am I the only one who knows that? I mustn't. Did anybody else know that electrons travel in waves? You knew that. Do you know electrons have? Yeah. Do you know electrons have a mass? I mean, it's so tiny. It's got so many negative, powers after it. You wouldn't see it, but they are a mass. Right? You can take an electron and destroy it and get some energy out of it, which is usual test for an object that has mass. Can it be turned into pure energy if you destroyed it? So we don't move like waves, yet we have mass, but electrons seem to, which in my brain contradicts the universe, but what do I know? The fact that you can't go faster than the speed of light screws with my head. You know, you can't go faster than the speed of light.
Yeah, it's because of how much energy it takes to accelerate. So if you have mass, it's going to take an infinite amount
Of energy to move. And there's some other time dilation things. When you get into Einstein's theory of relativity and black holes and stuff, it's really cool, but kind of unbelievable. But that's only because we judge the universe by our senses and what we believe makes sense, and evidently all of those are wrong. Right. I'm looking at some questions to see if I have any real issues here, and I'm not seeing any. Would you agree that just as I'm on this one, would you agree 17 is just a matter of finding some partial derivatives? Right. There's nothing major here, isn't it? Just power rules, nothing to see here. Do you see Clairaut's theorem? Right, boom, boom. Now it says here, there are very few questions like this, but there isn't a box where you normally put your answer. What I would do here is I'd write down what uxy is, and then underneath it, write what uyx is, and then underneath that, say, see, I've proved it. So if you take this function and differentiate with respect to x, and then use that answer and differentiate it with respect to y, you will get the same answer if you do the process in the reverse order. You do the y first and the x second. Is there any problems with question 19? Do you feel comfortable about all the bits and pieces? Do it twice using r. Do it twice using theta. Do it once using r and theta. Would you assume that this answer will be the same one as that? Would you agree? And that's essentially Clairaut's theorem. So whatever ugly answer this is, you can save yourself some time and put it there. And the reason for that is that I can look at this function and I can be pretty comfortable. There isn't anything weird going on. Would you agree? It's just a normal function that's continuous. And Clairaut says it's continuous. Right, there's that horrible guy with the inverse sign I was talking about. Now they've got a little kicker in the tail, which I haven't talked about, but I think you should be able to figure it out. Once you differentiate this thing with respect to y, won't you then plug x equals 3 and y equals a 6? And your answer in here is going to look like, I don't know, 14 inverse sine of 3 or something, right? It's just going to be a number. Does that make sense? You're just going to do a partial derivative, and then when you're finished, you're going to replace the x and y by values, and that's going to be the final answer. If anybody is looking at the homework, is there anything I've skipped or you're not sure about that I should do? Because I want to move on if we're done with this.
For the verifying the Clairaut's theorem,
Yeah.
do you just want us to type out an explanation?
Well, I was just saying, I'll pretend this is the answer. I know it's not. I would write down u of xy equals 5x squared plus 5y squared. U of yx equals the exact same thing. I have now proved, or I've now shown that it holds. I haven't proved it, but I've shown in this example it works. Right, so just find the two partial derivatives and prove they're equal. And just type that in here, just like you would type an answer in here and type it. You know, can you imagine you do this when you type the answer, you did this when you typed the answer. All I'm saying is just do the same here. And then at the bottom in English saying, look, I've shown that Clairaut's theorem works, at least for this question. I'm scanning through. I've done triple derivatives, right? So we know how to do x, y, and z. Quotient rule, power rule. Oh, maybe I should do this one. I'll not do that particular one, but I will do this question. I know that I talked about implicit partial differentiation, but I'm pretty sure I didn't do that many examples, and I certainly didn't do any weird ones, which this one is. Suppose the question asks us to find this partial derivative. So it's implicit differentiation. So that means that we have to think of z as a function of x. Well, e to the 3z gets you e to the 3z. But then don't you have to differentiate 3z with respect to x? That will get you 3 dz by dx's. Can you imagine doing e to the 3y in Calc 1? If you differentiated e to the 3y, wouldn't you get e to the 3y times 3 dy by dx? You see the equivalency. Is it ringing some bells? Way back in the day. Now, this has to be treated differently than it typically would do. Since z is considered a function of x because of this being written, what we really have here is a product rule. And I'm going to call this f, and I'm going to call this g. So it's going to be f dash g plus f of g dashed. If you differentiate this with respect to x, that is still considered a constant, so you get that. You leave the g alone. If you take this fella and you differentiate, take this guy, leave him alone first, and then this guy and you differentiate it, you do get 3z squares. But what else do you get because it's a z? Suppose I differentiate. Say again, sorry. What would you get here?
Shouldn't it be another z?
It should be that kind of z. If you differentiate y cubed, implicit differentiation, don't you get the derivative of y cubed finishing with a dy by dx? If you differentiate a z cubed, you'll get 3z squared times the partial derivative with respect to x. That's what implicit differentiation does. In this question, since you're being asked to do this derivative, the rules have changed. Normally in partial derivatives, one guy's a variable and all the others get treated like a constant, right? That's a typical way of doing it. But in implicit differentiation of any kind, the variable, in this case z, is now considered as an x. So there's two variables going on here, z's and x's. That means this y squared is the only guy that I treated like a constant. Everybody else get treated a little bit differently because of that. Now, if you take this side here, right, and you tidy it up, you don't get much tidying up, but you get that. On this side, you're going to get y squared z cubed plus x, y squared, z squared, stick a 3 at the front, dz by dx. Now remember, the goal in this question is to find the partial derivative dz by dx. Right now, don't we have it in two different locations, right? We have some of it here, we have some more of it here. So what do I do next to kind of get things closer to the answer?
Group like terms?
We could, but how am I going to group them then? That sounds, might be a good idea.
Subtract the 3xy squared z squared from
All
the
that stuff. Yeah, that's exactly what you do. Okay, I know it's a bit messy, but move my equals over. What do I do next? Essentially, what do I do on the left-hand side?
You pull out the dz/dx.
As a common factor, and that leaves me that guy. You know, I should wait till I finish before I figure out where my equal signs go. And to finish with, then, don't we take that guy and divide them into both sides? So this fella is a y squared z cubed over 3e to the 3z, take away 3x, y squared z cubed. That's the answer. Now, I have not broken the rules that there's one variable and the others are treated as constant. But you only do those when the function is written like this. But when the function is written like this, then you have to do implicit differentiation. So can you see, if I wanted to do dz by dx here, wouldn't it be x is the only variable in Trown, treat y like a constant? Whereas if I had to do this one, where there's z's in various locations, isn't this an implicit equation? And therefore I have to use implicit differentiation. And so if I'm being asked to find the same guy, do you see that the approach has to adjust? Right. You got a z squared. You got to do something with it. Z has been considered a function of x, so you have to differentiate it according to the rules. Okay, I hope that didn't distract you more than help you, but there is a question that looks pretty bad that technique's going to get used. We've finished everything that we need to do for your homework, but I want to get started on the next section. And excuse me, close off for a second. I've got so many buttons to do. Where are you? You can just bear with me for a few moments more. It's in here somewhere. No, you can never find things when you want them. Never mind, I'll use a textbook. I've got a PDF of that, that'll do. Okay, I'll go back out and in. With a bit of luck, you'll actually get to see this darn thing. I've lost you. Oh, you're over there. Oh, there's anything in the chat I should know? Okay, bye-bye, Olivia. Good luck with your exam. Okay, let's kick in here. And oh, it did appear. Good. Right, I'm minimizing some bits and pieces, or at least attempting to, and failing miserably. Okay, can you see infinite sequences and series? That's what I was fighting my way through. I don't know how big it is because I've got these side panels, and normally you should just click there and they move in. But evidently, I don't know how to click things, or maybe when it's in this format. So I am just going to do it old school. I was going to use them because they're kind of cool and they draw pretty pictures and things, but oh heck. Our last chapter, chapter 11, deals with sequences and series. Technically speaking, infinite sequences and series. One definition of what is mathematics, when you study that subject, what are you studying? And one definition would be that mathematics is the study of patterns and relationships within variables and numbers. Patterns and relationships. Relationships could cover things like functions, right? What we haven't looked at so much is sequences and series, which are patterns with just numbers, typically. So, this is an intro, so I just want to get as much of the vocabulary out the way. That's a list of numbers that has a pattern to them, right? That's called a sequence. When you have a sequence, this is obviously called the first term, this is called the second term, third, fourth, and fifth. For some reason better known to themselves, we tend to use the letter U with a subscript. So for instance, U3 in this particular sequence would be a 5. Now, if a sequence is a list of numbers that has a pattern to them, and it has to have a pattern, or it's not truly a sequence, it's just a list of random digits, right? If it doesn't have a pattern, right, it's just random, right? The next number could be anything. A sequence has a pattern to it, that is helpful. And when you have a pattern, you can sometimes generate a formula. Now, if you think of n as being the position, this is U1, so that's n being 1, this is n being 2, this is n being 3, this is n being 4, and then it's being 5. And you can imagine you randomly choose a guy, and you're going to call it n, right? The nth position in a sequence. Could anyone come up with a formula off the top of their head that would tell me how to get the nth number in this sequence? So if you plug in 4, the answer 7 needs to appear. If you plug in 5, the answer 9 has to appear, and so on.
Two n minus 1.
Nailed it. How did you do it? Just try to delve into your brain, your workings.
I just found an n number and then multiplied it by 2 because it was patterns of 2 and subtracted 1 to get the answer.
So patterns of 2 allows you to come up with the 2n bit. Why wasn't it just 2n?
Because then it would be even numbers.
Okay, it didn't match the data. Right.
Yeah.
How about this sequence then? Now, in this one here, what you said made perfect sense to me. Do you notice that the gap between each number is 2? Just a different way of saying what you said. Have you noticed that in this one the gap's 4? I can create, maybe you can for me, what the formula for the nth number in this sequence would be. And I've given you a little bit of clue. There's going to be a 4 in the formula.
4n plus 1.
And I'll explain the 4 part. When you have a sequence that's made up of any number, it doesn't need to start at 1. You know, over here it started at 5, right? You can start any way you like. But once you start with that number, you just continually add the same amount. In this case, you add 2s. In this case, you add 4s. Those formulas are always going to start with, in this case, 2n, and in this case, 4n, right? That's how the deal works. Then all you need to do, don't you, is basically tweak it to make it fit. So would you agree that if you plug in 1 here, don't you just get 4? But the first number has to be 5, so you see how you fix it. This particular sequence is called an arithmetic sequence. So let's look at another one. Give me a number between 0 and 10. Well, 1 and 10, I don't. 9. Give me a nice small number to keep adding.
3.
So I'm going to go 9, I'm going to go 12, I'm going to go 15, I'm going to go 18. Would you agree that's an arithmetic sequence? It has, you start with some random number, and then in this case you keep adding 3s. Now, since you keep adding 3s, you go 3 in. And what I typically do is I go to the first number, and I say, okay, if I plug 1 in to this formula, what do I get? And the answer is I just get 3. But I don't want 3, I want it to be equal to 9. So don't you just adapt? So you see we have a pretty, a pretty simple process for getting the general formula or of arithmetic sequences. Don't you just find out what the gap is, and that tells you the constant, and then you go to the first one and you make sure it works, and if you make that one work, all of them work. I'll give you an example. That's the 4th one, right? It's 18. 3 times 4 adds 6. 18, right? Works for all of them. Well, that's an example of an arithmetic sequence. They're pretty common. Some sequences get names because they are common or because they're useful. This next one is called the Fibonacci sequence. Excuse me. I'm sorry. I'll see you later. I think she was wanting attention. Right, Fibonacci sequence. Anybody seen Fibonacci? God, I can't be the only one, right? Let's go for it. Anybody remember what it starts with?
0, 1, 1, 2, 3.
Okay, I'll do a different version of yours, but the 1, 1 is fine. So 1, 1, 2, 3, 5. Now, there's definitely a pattern here, but the pattern isn't you add the same amount, right? You're adding different amounts. What would the next number be in this particular sequence?
8.
8. Now, Fibonacci sequence is just it's like a fun sequence. Obviously, the Italian mathematician Fibonacci played with it. I've been told that it actually appears in nature. Branches of certain plants branch according to that pattern. Kevin, you've heard about that?
Yeah, just a little bit.
Yeah, it's just, sometimes nature imitates math or math imitates nature. It has some interesting properties. The first thing is that it's probably not a good idea to try and create this formula because it really doesn't work well. So what do you do in Fibonacci sequences? You do what's called a recurrence relation. And in the Fibonacci sequence, at least in the textbook that I'm used to, you do it by this. This is called a recurrence relationship. And basically this is saying your two start numbers are 1 and 1, which they are. I can't vouch for the fact that why that's called U0. It depends on the textbook. Sometimes it'll be called U1, but that's the one I'm more familiar with. You start with 2 root numbers. And then it says the next number, UN plus 1, is made up of this number plus the one before it. So for instance, U2, U3, U4, U5. If I called this U5, U5 is made up of U4 and U3. And that's what that's saying. A Fibonacci sequence has some weird properties. Do you know if you take two consecutive numbers in a Fibonacci sequence and you divide this one by that one, that the limit as n tends to infinity is the golden ratio? You know the golden ratio, the ones that the Greeks built all their buildings to, right? It's a ratio between the length and the height of a building that was pleasing to the eye. The Greeks even knew about it. That's diverging a little bit, but it's cool to know stuff. Some sequences have formulas that are written down as recurrence relationships. It's just what they are. But that one's called a Fibonacci sequence. The next sequence is called a geometric sequence. I'm just going to pick a random number, 3. That's going to be my first number. That's going to be my second. We're back to the usual labeling. What would the next number in that sequence be? Just looking at patterns.
48.
Would you agree that you just doubled the previous number?
Yeah.
Now, if I wanted to give you this formula, I can do it as a recurrence relation. I can tell you that the next number in the sequence is double the one that came before. And then I just need to tell you who the first guy is. And that is the formula that would allow you to generate that. Basically would say, start at 3. If you want the next number, double it. If you want the next number, double what that is. If you want the next number, double it. The big problem with recurrence relations is, if I asked you to find u of 100, God, I wouldn't ever ask that. If you use this, wouldn't you basically just have to keep doubling until you got to the 100th term? And that would take you forever in a day, and you wouldn't really be very happy about it. Do you know that's the same thing is true if you had to do the Fibonacci sequence and I wanted to know what the 100th term was, U100? Wouldn't I have to find the first 99 first before I could get to the 100th? So it would be nice, wouldn't it, if we can get formulas that are written not as a recurrence relation, but an algebraic formula. And this is how you get geometric series. A is the first term, so A will be 3. R is called the common ratio. In this case, the common ratio was you doubled each time. So UN is 3 times 2 to the power of n minus 1. I like to put brackets around this because if you write it like this, doesn't it look sort of like 32 to the power of something? Well, it does to me. Even if you put a multiplications symbol, doesn't it sometimes just look a little bit weird? And you might mistake it for 3.2. So I would suggest you put a bracket around it. Now, I've just told you that that's the answer, right? Let's prove it to you. Let's do a geometric sequence, right? You start with A, great? So U1 is A. Now, don't you multiply it by a fixed amount, which we'll call R. So won't this be AR, and that's what U2 is? What would the next one be? Well, wouldn't you multiply it by R, and you get AR squared? And if I do one more, 4, won't you get AR cubed? Do you notice that there's a direct connection between this number and the power of R? So if I wanted UN, wouldn't it be AR to 1 less bar? That makes sense? I'm looking for some reactions, but most of you have hidden your faces, which really screws up my ability to tell if I'm getting the point across. But thumbs up are good. Thank you for helping. Right, so let's do a geometric sequence from scratch. Give me any number between 1 and 9.
7.
Okay. Give me a small, nice number to multiply by.
21.
4. Okay, so 28, 112, 448, and forever, right? So this has the feature that a geometric series has, right? You start with a number, and then you just keep multiplying by 4, right? Which means that what they call A is 7, and what they call R is 4. So the general version is AR to the n minus 1, 7 times 4 to the power of n minus 1. And if you wanted to know what u to the 100 is, wouldn't you just do 7 times 4 to the power of 99? And no, I'm not doing it because that number would probably not work because it's so big it doesn't fit in the calculator. But at least isn't that the calculation for doing it? And you can plug into a computer and it could handle it. We call with sequences. They're just a list of numbers that have patterns.
Yep.
Yeah. So let's look at another sequence that's special enough to get its own name. It's called a harmonic sequence. Now, harmonic sequences have only one real typical pattern, and that is that you go plus, minus, plus, minus, plus, minus. And you tend to do harmonic sequences in conjunction with one of the other sequences we've talked about. So I'll give you an example of a harmonic sequence. You could go 1, negative 3, positive 5, negative 7, positive 9, negative 11. Do you see that's basically a geometric sequence where we've alternated the values to being plus, negative, plus, negative? That's a harmonic one. But there's one very interesting.
Did anybody else freeze?
Uh-oh. Have I froze?
You're fine from my end.
Okay, looks like just one of you has an issue. This is a very interesting one. Which actually tends to be the only one that they do. But technically speaking, any harmonic sequence, this is just a special one. This is, in fact, the one that they almost always deal with. But couldn't I do a geometric sequence and just go back to it and make plus, minus, and want to become a member of the harmonic sequence family, right? But this particular harmonic sequence is quite interesting because when you look at the positive version of it, there is a rather disturbing fact, and they discovered this really early on. This is a sequence. There's a thing called a series. A series is what number, and I'll use that vaguely, what number you get when you add all the terms of a sequence together. So a series is just one number. And let's return to the ugly part. This guy here, which is all the positives, which is a very special sequence. You can take this guy forever. You can imagine what the term is, right? It's, you know, 1 over n plus 1, right? It'd be a very easy formula. Would you agree it's getting smaller and smaller and smaller? Now, they typically use S to mean the series. And if you add this guy together to the end of the universe, do you think it adds up to a specific number, like 42? Or do you think that the answer is infinitely large? In other words, it just gets bigger and bigger and, you know, it has no finish. Because that's your only two choices. Is that an infinite number? Or is that a finite number? And it could be a billion, but it's still finite.
It's
It
a
appears
finite
it's-
number.
Say again, first, James, what did you get?
I think it's a finite number because your value is reducing the entire time. So you're approaching 2.
I hear you. And there was another comment. I didn't catch who it was. What was your thoughts?
Oh, it approaches a specific number.
So you both agreeing that the logic of what you see means that it should approach a specific number.
Yeah.
This is why it freaked him out. It's infinite. And intuitively, that does not, what you said is exactly what 99.9% of the world thought. They think, but surely it's getting smaller. It should add up to a number like 2. Well, there is a guy that does that. That geometric sequence, right, when you add it together, that's called a geometric series. When you do that, that guy does end up adding up to 2. This guy, who looks very like him, is getting small, adds up to infinity.
Is
And
it
this is
the difference between, we learned it in Calc 2 last quarter, where it's if the function closes fast enough, it'll go to a finite number, and if it doesn't close fast enough, it'll go to infinity. So the first one just doesn't close fast enough to stop, and the
exactly.
I forget the exact term for it, but the bottom one there closes fast enough that it stops at a number.
Yes. So that's a very nice way of saying it.
Yeah, because they technically both go to infinity, but the
Oh, no. This one
Well-
does not go to infinity. It has an infinite number of terms, yes. But if you add them up, that
It'll equal
total
2.
has a limit of 2. Technically, it has
Okay.
a limit of 2, right, if we're being lawyerist about it. This has a limit of infinity, and this has a limit of 2. Now, this is not a formal proof, but can you just kind of go with the flow here? If you add up these 4 guys together, you'll get an answer that's a bit bigger than a half. Would you agree? I mean, it's a half plus 3 more. It's a bit bigger than a half, right?
Yeah.
So I'll call it a half plus. If I wrote down the next 8 terms, right, so that'd be from 1/6 to 1/14. If you add them up, can you trust me that it comes to a total that's at least a bit bigger than a half? Then you add up the next 16 terms, and all of them give you an answer that's a little bigger than a half. And you continue this process of adding up twice as many terms as you did before, and each of those is bigger than a half. And you can do that to infinity. So can you see what you end up doing is you're ending up an infinite number of things that are all a little bit bigger than a half. And what would an infinite number of halves get you? Infinity.
Infinity, yeah.
Now, this one here, what time did we finish? 9:30? Right, good. Now, this one here is called a geometric series. You tend to get your name, the series name, from the sequence's name. So if it came from an arithmetic sequence, it would be called an arithmetic series, right? If it came from a geometric series sequence, it become a geometric series. So that's kind of the naming. This one adds up to 2. And this one the Greeks knew about, and they had a story for it or a version of it. And this one freaked the Greeks out. There are different versions of it, but it looks something like this. The Greeks used a version of this that proved that if you shot an arrow in the air, it couldn't move, which freaked them out as well, because the logic seemed very good, but reality told you different, right? You shoot an arrow in the air, it moves. But essentially, it's to do with having the time interval, and the thing has only an amount of time. So here's a story that from here to here is 2 feet long. And here's a little frog. That doesn't even look like a frog, does it? There. Here's a little alien frog. And it was wanting to get to the water well. And it had a bit of a problem, because every time it jumped, it only jumped half what it did the previous time. So it does its first jump, and it goes a really good jump, and it got a foot. And it was happy. And it was closer to the well. And then it took its second jump, but unfortunately it could only jump half a foot. And then it had its next jump, and it was a quarter foot. Isn't all the jumps that it did basically this geometric series? And the problems the Greeks had was that the Greeks did not have a good concept of infinity, and it tended to generate things that didn't make sense. So the Greeks were puzzled by this problem, because it went and said, will the frog ever reach the well? Now the math, which we can show you later, is, and I can prove to you, maybe I'll prove it today actually, that this adds up to 2, right? So the math said it adds up to 2. And that means it reaches the well, right? Because the well's 2 feet away and it adds up to 2, it reaches the well. But the Greeks also were saying, wait a minute, at any given point in time, isn't the frog a little bit away from the well? And won't it only jump half the distance to that well, each jump? So yes, it's getting closer, but isn't there still a little bit to go? And so their logic was saying that that poor little frog should jump for eternity and never reach the well. But their algebra told them it would reach the well. And there's a contradiction there. And yeah, the Greeks, the great mathematicians that were too fixed in some of their ideas, and therefore they couldn't adapt when things didn't fit. They just had stories saying, it doesn't fit, but I don't know what to do about it. It kind of worried them, but they didn't have a cure. Distracting a little bit. Do you know the Greeks had no idea of what the square root of 2 was? Because the Greeks had the false idea that no matter what the thing was, everything could be written as a fraction, as a ratio. Everything. No matter what it was. And you know that the square root of 2 cannot be written as a fraction. It's called, I think it's something to do with completing this, the unit square problem, right? What's the diagonal of a unit square, right? The Greeks had this puzzle. How long is the diagonal of a square whose sides are 1? Now we know the answer is root 2. And the Greeks tried and tried and tried to find the fraction for that answer. And they failed miserably. And they couldn't figure out why they failed. And the reason why they failed is that the answer is not a fraction in the first place. And you might think, and they did. They were thinking, look, couldn't you have any number in the world as your numerator and any number in the world as your denominator? Surely there's enough variation in there to do anything. Right? So 1.414, right? You know, the decimal version, approximate of root 2. Couldn't that become a fraction with a little bit of effort, right? And it threw them. This one threw them. It was because they hadn't the concept that things aren't always fractions. They had a poor concept of infinity as well, because they were relying on human experience. And do you know sometimes math tells you things that make you, that contradict your life experience? So I'm about to prove to you that 1 plus a half plus a quarter plus an eighth for eternity has a limit of 2. because the Greeks never had the concept of limits. They didn't understand it. They'd never developed them. That came later. So here is my proof. If you take this guy and you add him to infinity, which is fine, right? Okay. I can take that guy, agreed. Now, suppose I wanted to find half of this guy. Wouldn't I just half what it's made up from? Oops, and I'll rewrite it like this. If this is S, won't a half S just be half of all these, which is this? Agreed? Now, if I take the top and subtract the bottom, don't I get a half S? If I take the top and subtract the bottom, don't these all kill each other off? And the only thing that lives is 1. And if I double both sides, we can do this because we have the concept of limits. I'm not using the word limits, but the proof, you know, this is just a pseudo proof, but the real proof has the language of limits attached to it, and it works totally fine because of that. Now, can you imagine how difficult it would be to try and convince ancient Greek mathematicians that you could add an infinite number of things together and still get a finite answer? Because isn't your common sense saying if you keep on adding stuff, it just keeps on getting bigger and bigger and bigger, right? Well, technically it does, doesn't it? It gets a little bit bigger each time, but only a little bit bigger, not infinitely bigger. I think that was kind of interesting. So right now we've got an intro to what we call sequences, and we know that when we get series, we add them all up, and sometimes you get a nice answer and sometimes you don't. That one is bad news. This one is going to throw you. Oops, I'm out of sequence. I'll do it again. This harmonic fella, this is the basic building block of all the harmonics before you do a plus minus on them. This guy adds up to infinity. What about, oh, darn it, in space? There. Plus minus, plus minus. What do you think this one does? Infinite or a number? What does this series add up to? It doesn't matter if you're wrong. What does your conceptual feeling make you think?
It gets closer to a finite number.
Good. Would you agree? This one is getting bigger, but isn't this one getting bigger and then less and then bigger than less? And it's a kind of ziggy-zag kind of thing, and you would expect it to level off. You agree? And it does. If you leave it in this order, I think it levels off to log 2. That's my recollection. I'm pretty sure it's log 2. Quite hard to prove, but we'll actually get to prove it. Chapter 11 is going to deal with sequences in a very minor way. We're not going to spend a lot of time on it. It's going to spend a lot of time on series. And basically, proving that they converge, which means they add up to a finite number, or proving that they diverge, which doesn't always mean that it adds up to infinity. So just, there are 2 basic families of series. They're the ones that converge. And when they converge, we're basically saying they have a limit that is a number. So like the poor frog, the answer would be the limit is 2, right? We have to really use the language of limits when we add series, but apart from that, that's it. And then you have the guys called diverge. And diverge would be things like 1 plus a half plus a third, right? And diverge can mean that S is infinite, which basically means its limit of S is infinite, right? But here's a diverger for you. There's a sequence. Not a very interesting sequence. This is its series. What does it add up to? Yeah, it's kind of hard because doesn't it depend on where you stop? Edward, what you say? Can't hear you,
It
Edward.
oscillates between 0 and 1.
Right, depends on where you stop, right? If you stop in some place at 0, if you wait to the next term to stop, you've got 1, which is not really very helpful because where is infinity? It's not a fixed place that you can stop at, right? There's not a stop on the number line called infinity and then you stop there, right? So basically, if you plotted what S would look like with just the first 3, 4, 5 terms, what you'd find out is that it would be at 1, and then the total would be 0, and then the next time it would be 1, and then it was 0, and then it'd be 1, and then it would be 0. And wouldn't you be getting this infinite zigzag? And doesn't that mean that the limit doesn't exist, right? There is no limit as n tends to infinity. So when we talk about diverges, what we're really saying is the limit as n tends to infinity of the S guy does not exist. And in this situation, aren't we saying the limit is infinity? So diverges have like 2 flavors of them. Converges only has 1 flavor, right? Converges means that they add up to 42, right? And that's it. One answer, that's what they add up to, right? Technically speaking, its limit is 42. We good? Then, how about looking at what should we do? I'm going to finish early today because I just want to do one last thing and then get some questions because I think this would be a good place to stop. We've covered all the generic terms. I'm trying to think of one. There's some in the back of my head I know I want to do, and then that's the end. It'll come to me in a minute if I think hard enough. We've done the sequences. We've done the series. We've talked about convergence. We are good. We are back to sequences again. Suppose you tell me the formula for a sequence. In fact, most questions, that's exactly what they do. They tell you the formula. I'm writing it this way. So for instance, if I gave you this sequence and I said to you, I'd like to know what U5 is, don't you basically just say 5 squared plus 1 over 2 lots of 5 take away 1, that's 26 over 9, and that's your answer, right? Suppose I asked you, what's the limit of a sequence? Then essentially I'm asking you to solve this problem. Agreed? Now, if you have a limit of a sequence and it's a number, doesn't that just mean if you keep going on to the end of the universe, the numbers start getting closer and closer to this one value, right? And if it diverges, don't the numbers just go off to infinity, or they oscillate between 2 numbers, or they do something else, right? The question is, how do we solve these problems? What math techniques do we use to solve these problems?
L'Hospital.
L'Hopital. I call it brute force. Do you know the one where you divide the top and bottom by n and then you make n infinite, right? Those are the two most likely, because in these questions, aren't this bit here always going to be the same, right? You're not going to have the limit as n tends to 2, right? It's always going to be infinite. It's also going to be positive infinite. In this case here, I could do L'Hopital, which works fine. If I chose to do L'Hopital, then that guy would get me 2n. That guy would get me 2. Wouldn't it be the limit as n tends to infinity of n? Wouldn't that be infinity? In which case we would say it diverges. Great. On the other hand, if I went and said, what's the limit as n tends to infinity of... I'm trying to think of something. You know, that ugly looking thing. I could do, sorry?
It's going to converge because it's both n squared on top and bottom, so it'll reach a point.
Right. Would you agree that it would basically become a half? I've cut out a lot of math, but you can tell that. Isn't there a rule that you can actually ignore the square root and just do the limit of the inside, which is where that came from, and then take the square root of the answer? It's a convenience. Otherwise, you'd have to do I wouldn't want to do that with the square root involved, because wouldn't that cause some really ugly L'Hopital rules, for instance? So we would use divide top and bottom by n or n squared or L'Hopital typically. And if we get an answer that is equal to a number, then we would say, the jargon is, we would say that that sequence converges to a half. And if we get any other weird answer, we would just say that it diverges. And not every single sequence do you need to do this. Do you know the one that went 1, negative 1, 1, negative 1? Couldn't you simply just say that that alternates between two values and therefore has no, it diverges? Diverges just means it doesn't have a numerical limit, right? So it's a catch-all phrase. It can mean infinite, but it can mean it just doesn't have an answer that you can home in on. That is us for today. I think we've learned